In this video, we introduce polar coordinates and polar equations. So we're going to start by talking about how to find the polar form of a point given in Cartesian coordinates, and then we'll talk about how to convert between the Cartesian and polar forms of a point. Next, we talk about how to graph points on a polar grid. Then we talk about plotting polar equations and converting those polar equations to their parametric and rectangular forms. And finally, we look at a couple of very unusual sorts of polar equations. So it's all been divided up into chapters if you want to skip around. And we're going to start with our basic definition of polar coordinates. So here we're looking at the xy plane and we have a point given by the coordinates x, y. I see that that point has some distance from the origin, and that's called r. And it also makes an angle of theta with respect to the x-axis. So the idea with polar coordinates is that we could represent the same point with the coordinates r theta, telling you how far to go from the origin and what direction to aim. And we can write down relationships between r and theta and x and y by using trigonometry. First, I could apply the Pythagorean theorem and discover that r squared is x squared plus y squared. Then I could think about the tangent function here and say that the tangent of theta is the opposite over adjacent, in other words, y over x. And so these are the equations that give you the polar coordinates of a point in terms of the rectangular coordinates. I can go the other way around and ask what's x in terms of r and theta. And that's just the adjacent side of this right triangle, so that's r cosine theta. And while I'm at it, I'll put in the opposite side, that's r sine theta. And I've got the equations that give me the x and y coordinates if I know the r and theta coordinates. So before we work an example, I want to point out real quick that there are some ambiguities in these equations for converting to the polar coordinates from the rectangular coordinates. First, there are infinitely many points in polar form corresponding to one point in rectangular form, because I could just keep rotating by an extra amount of 2 pi in either direction as long as I want, and I'll keep arriving at the same point. Second, negative values of r are allowed, so I could just aim the opposite direction of where I want to go and then say that I move a negative distance, and I could arrive at the same point. In addition, if we find ourselves actually using the inverse tangent function to find the angular coordinate theta, the inverse tangent gives you an output between negative pi over 2 and pi over 2. So if you're in the second or third quadrants, you're going to have to adjust for that. Remember that domain restriction came from making the tangent function invertible in the first place. Whenever possible, you try to get around those issues by just thinking about the geometry that's going on. So let's take a look at our first example. We're asked to convert the Cartesian point 1, 1 to polar coordinates. And in part A, it says, use a positive r and an angle between 0 and 2 pi. So the point 1, 1, you may recall, corresponds to a 45-degree angle or an angle in radians of pi over 4. Again, I didn't have to explicitly use an inverse tangent function. I could just visualize where the point is and figure out what the angle is. And what about the r? It just comes from the Pythagorean theorem, and I can say r is the square root of x squared plus y squared, 1 squared plus 1 squared. And this gives me the square root of 2. So there's my positive r and my angle of pi over 4. And then when you're writing down the polar coordinates of this point, you're going to do it in the order r theta. So this is the point root 2, comma, pi over 4. Next, I'm asked to use a negative value of r and an angle between 0 and 2 pi. So what I want to do is face the opposite direction of the angle pi over 4. So in our graph real quick, the angle pi over 4 points that way. I want to point opposite to that and then go backwards by a distance of root 2. So what's that angle that faces opposite to pi over 4? That's just pi over 4 plus pi, or 5 pi over 4. And then I want to go the opposite direction of that by a distance of root 2. So my r value is going to be negative root 2. And I get the polar coordinates negative root 2, comma, 5 pi over 4, and I land at exactly the same point. In the second example, we're asked to convert from polar coordinates into rectangular coordinates. And for this, I just use my second set of equations here. The x coordinate is going to be r cosine theta, so that's 3 cosine 2 pi over 3. And 2 pi over 3 is a special angle, and the cosine is negative 1/2. So I get negative 3/2 for the x coordinate. And then my y coordinate is going to be 3 sine of 2 pi over 3. And the sine of 2 pi over 3 is root 3 over 2. So I end up with 3 root 3 over 2. So now I can write down my point in rectangular coordinates. And I get negative 3/2, comma, 3 root 3 over 2. So to make it easier to plot polar points, we can introduce a polar grid for the plane, and the lines I've labeled in here correspond to all of our classic special angles. I have pi over 6, pi over 4, pi over 3, of course an angle of 0 pointing to the right, pi over 2 pointing straight up. And in our example, we're asked to plot the following points that are given in polar coordinates. So remember that first number means how far do you go from the origin, the second number means which direction do you aim. In our concentric circles here, those are marking off distances from the origin. The first one is a distance of 1, second was a distance of 2, distance of 3, and so on and so on. 4 all the way out to 5. And in our example, we're asked to plot the following points that are given in polar coordinates. Now remember, the first number is the distance from the origin, and the second number is which direction do you aim. So in part A, I go 2 units from the origin in a direction of theta equals pi over 6. So I land right here. In part B, I want to go 4 units from the origin in a direction of negative pi. So negative pi, you imagine just rotating from the positive x-axis clockwise by an angle of pi. You landed exactly the same angle as positive pi. And I go 4 units, 1, 2, 3, 4, and I've got my point. So this is a nice reminder of the ambiguity with polar coordinates. I can represent the same point with 4 negative pi, or 4 positive pi, or even 4, 3 pi, or any other plus or minus 2 pi. In part C, I have a negative r, so we're going to go the opposite direction of where we aim. And the direction we're aiming is pi over 2, which is straight up. And then I go negative r, so 1 unit in the opposite direction of straight up. And again, to highlight the ambiguity with polar coordinates, we're asked in part D to plot the point 1, 3 pi over 2. Well, 3 pi over 2 is straight down. And if I go 1 unit in that direction, I land on exactly the same point as negative 1 pi over 2. Next, we're going to check out a polar equation. So I'm given this equation in the upper left-hand corner. R of theta is equal to 2 cosine theta. And I've already plotted this thing using a piece of software. And it appears to be a circle that's centered at 1, 0 that has a radius of 1. So in our example, in part A, we're asked to verify that this curve works by plugging in special angles on 0 to 2 pi. So I'll just erase a little spot here to do some of the work. And let's go ahead and start with theta equals 0. And I get that r of 0 is 2 cosine 0, and the cosine of 0 is 1, so I get 2. All right, so I'm aiming in the direction of theta equals 0, and I go 2 spaces. Well, this puts me right here, definitely on the circle that I'm looking at, so that's encouraging. Next, we have to go to some special angles where the r's are going to come out to be numbers that have to be sort of approximated with a decimal. If I go to pi over 6, that's this line right here. I get twice the cosine of pi over 6, and the cosine of pi over 6 is root 3 over 2, so I end up with root 3. Square root of 3 is something like 1.73. Is it plausible that that point is correct? It looks pretty good, because this circle is 1, this circle is a radius of 2. If I go to pi over 4, I get 2 cosine pi over 4. But the cosine of pi over 4 is root 2 over 2, and if I multiply by 2, I get square root of 2. Well, that's about 1.4. So I'm going to be a little closer to the origin along this line, a little less than 1.5 spaces, so that one looks pretty good too. Go to r equals pi over 3. Cosine pi over 3 is a half, so I get 1. And it looks good when I aim along this line of sight for pi over 3. I land right on r equals 1. R of pi over 2, the cosine of pi over 2 is 0. So when we aim straight up, we go a distance of 0 from the origin. So if we go to the next special angle, that's 2 pi over 3. In other words, we're aiming up this way. Well, how can we possibly end up back on this graph of this circle if we're aiming the wrong direction? When we plug in 2 pi over 3, the cosine of that is negative 1/2, and I get an r value of negative 1, so I walk backwards from that direction, a distance of 1 from the origin, and here I am. So the rest of these are going to happen in a predictable manner. I can fill in the rest of those special points, but the surprising thing is I end up completing my circle when theta gets to pi. Just plugging in that point real quick. When I aim to the left of the origin, that's theta equals pi. My result is that r is equal to negative 2, so I go 2 spaces opposite to that direction, and my circle is complete. So by the time you get to 2 pi, all that happens is you retrace the same circle. So r of theta equals 2 cosine theta on 0 to 2 pi is actually 2 copies of the circle that we're looking at. And this is going to play a role when we look at the parametric form of this curve. But first we'll do part B. we want the rectangular coordinates for this circle, so we should end up recognizing the equation for a circle at some point. We'll start with the polar form, and then I recognize that if I multiply the left and right sides by r, I get two things that I have handy conversion formulas for. R squared is x squared plus y squared, and r cosine theta is just x. So I gather all the terms on the left-hand side. X squared minus 2x plus y squared is equal to 0. And I can force this into the standard form for a circle if I complete the square on the x squared minus 2x part. That means I want to wrap up all of those variable terms in a squared binomial. But when I square that binomial, I get x squared minus 2x plus 1. In other words, I've made that 1 bigger than it used to be on the left side of the equation. To compensate, I have to add 1 to the right side of the equation. And I arrive at my standard form for a circle. X minus 1 quantity squared plus y squared equals 1. This circle has a center of 1, 0 and a radius of 1, which is what we see in the picture. Now what about getting the parametric form for this curve? To do this, I use my other set of conversions, x equals r cosine theta. And then I just plug in what r is in terms of theta based on the original equation of the curve. So r is 2 cosine theta. This gives me 2 cosine squared theta. Now it's not wrong to leave it in that form, but we're going to see something more interesting if we go ahead and use a trig identity on this. Cosine squared of theta is 1/2 1 plus cosine of 2 theta. And my 2's cancel. And I find that x of theta is equal to 1 plus cosine 2 theta. So here theta is the parameter for our parametric equations. I do the same thing for y, and r is just 2 cosine theta. And I use the trig identity on this, that 2 cosine theta sine theta is the sine of 2 theta. And I've got my parametric equation for y. So if you've recently studied parametric equations, you should recognize this as the equation of a circle where the center is 1, 0. So again, it's the same thing that's in the picture. But the interesting thing about the parametric form is we've been able to highlight the fact that it gets traced twice as theta goes from 0 to 2 pi. So as theta goes from 0 to 2 pi, these arguments go from 0 to 4 pi. In other words, we're doing 2 complete oscillations of each coordinate, and I'm drawing my circle over itself twice. Finally, we're going to look at a couple very unusual polar equations, but they do pop up from time to time. The first example is a polar curve given by theta equals a constant. And in most graphing software, it won't even let you graph this because they want you to solve for r. But what does theta equals a constant mean? This is giving us no restrictions at all on the values of r. R could be anything you want as long as theta is always pi over 3. So I just aim in the direction pi over 3, and I can walk forward as many spaces as I want, or I could go backwards as many spaces as I want, and it traces out a line passing through the origin, making an angle of pi over 3 with the x-axis. So how do I get the parametric form of this curve? I can write down x equals r cosine theta, and theta is always the same thing, pi over 3. Cosine of pi over 3 is a half, and so I end up with 1/2 r. And here, r is the parameter, so I end up with x of r is 1/2 r. I do the same thing for y. Sine of pi over 3 is root 3 over 2, and I end up with y as a function of r. And there's my parametric equations for the line. In part B, I'm asked for the rectangular form of the curve, and probably the fastest way to do this now would just be to take my y equation and divide by my x equation for the parametric form, because the r's are going to cancel. So I get y over x is root 3 over 2r divided by 1/2 r. You can multiply the top and bottom by 2 and get rid of those, cancel the r's, and I end up with square root of 3. Now writing this in the standard form for a line, I get y equals root 3x. So this is a line with slope root 3 passing through the origin. In our next example, we get another unusual type of polar curve, and that's where r is equal to a constant, but there's no restrictions on theta. So r is always 3, no matter what way you aim. The distance from the origin is 3. What we're describing here is a circle of radius 3 centered at the origin. So I could write down the rectangular form of this just by remembering the equation for a circle centered at the origin. But what I'm asking for here is a coordinate conversion sort of formally. And remember, one of our formulas was r squared is x squared plus y squared. I'll go ahead and put the x squared plus y squared on the left side to make it a little more recognizable. And r squared, well, r is just the constant 3, so I get 9. And I get the equation x squared plus y squared equals 9. Just the standard equation for a circle of radius 3 centered at the origin. What about my parametric equations? Again, I go to x equals r cosine theta. And r is always 3, and there's no restriction on theta, so x is 3 cosine theta. Do the same thing for y. And so I end up with the parametric equations, x of theta, so theta is the parameter here, is 3 cosine theta. Y of theta is 3 sine theta. And again, if you've just been studying parametric equations, which is the usual sequence of topics in Calculus 2, you'll recognize that as the parametric equations for a circle centered at the origin with a radius of 3. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.